My name is Chuck. I will be hosting the webinar today. This is a NABCEP accredited, CE credited course. So in order to get your NABCEP credits, you do have to stay for the entirety of the course. And we will provide an email address at the end where you can send an email with your name, how you want it to be listed on the NABCEP credit. And we will reply to those emails, hopefully by the end of the day, but certainly by the end of the week, depending on how many requests we get. So good morning, everybody. I appreciate you checking in the Q&A. This is a webinar format, so unfortunately, we will not be able to have you raise your hand or speak. So Q&A is definitely the way to have any concerns, questions addressed. As we go through the webinar, Daniel here, my coworker, will be able to answer some of those questions live and save some of them for a lively discussion at the end.
Good morning, everyone. Hello.
Good morning, Daniel. With no further ado, we'll go ahead and get started. This is the Simplify Elite IQ Installer Training, known as Battery Chemistry 101. Once again, it's NABCEP CE credit available for attendees who complete the entire webinar. We'll give you an email at the end to send your name, how you want it listed on the certificate. So a little bit of company history and overview about Simplify. We started out in 2010, known as Optimized Energy Storage or Liberty Pack. We were making batteries for the film and broadcast industry. And if you saw that movie Tron, where they had the light up suits, our batteries were part of that special effect. The other industry that picked up on lithium-ion was the military, and having some concerns about lead acid batteries and generators on the front line. They looked at lithium-ion, but weren't thrilled with the track record of safety. We were able to demonstrate to the Department of Defense that we were a safer chemistry. And through rigorous testing, we were deployed to forward operating bases and really proved that we were a safe and effective chemistry for the military to use. In 2013-14, we started to kind of expand the product line into what you're probably more used to now. There's an early battery cabinet shown there. 2015-16, we relaunched as Simplify Power using the name that you're familiar with and the logo. Really kind of changing the product mix even more, adding the access cabinets. Still concentrating on the lithium iron phosphate as a battery chemistry presentation. We're going to come back to that chemistry a lot. 2017 to 2020, we started to ramp up production, including a new warehouse and research and development facility. And then most excitingly, in 2021, we were acquired by Briggs & Stratton, bringing their numerous years of manufacturing experience to leverage our products in a new and exciting ESS, where we've got a vertically integrated battery, inverter, and monitoring system, all under one brand, Briggs Stratton Energy Solutions, the Simplify brand you're familiar with. We've also got new products on the market, including a high voltage division. So you can see that container in the bottom right corner. Those are high voltage batteries that could be used for a 277 480 volt commercial application, where our low voltage product, while definitely a solution for any size, may not be as practical. There you go, high voltage, and you can start to do megawatt hour size stacking. So Simplify has been around for 10 years or 12, 13 years now. So we've got a long track record that we're bringing into this industry and as we expand into other product lines. Well, why have we been successful? Well, we've got three main points. Safety. We use a non-toxic, non-hazardous battery chemistry. What does that mean? Well, it means that there isn't cobalt in it. And we'll really dive into how these different chemistries with cobalt affect safety over the next hour. The primary difference is that we do not have the risk of thermal runaway with propagation. Because of this, we're able to get a bunch of UL certifications, and I'll go over those in the next slide: 1642, 1973, 9540, and then all of that is culminating in the 9540A test. We have some UN Department of Transportation certifications that allow you to airship our product domestically in the US, which is uncommon to say the least, but it comes from our safety track record. And we are also available for many incentive programs, including in California here, the SGIP rebate program. Like I said, over a decade, we're coming up on 13 years now in 2023 of experience and growth. You know, for a product that carries a 10-year warranty, having a company in business for over 10 years is remarkable. A lot of products are out there offering a 10-year warranty, but have been in business for 3 or maybe 5 years. So they don't have products out there that are at or past their warranted life. Well, we do. I also answer the phones and tech support, and I get calls about our early OES batteries. They're still out there. They're still working. We're deployed in more than 45 countries with something over 250 megawatt hours installed worldwide. Like I said at the top, we were tested and validated by the US Army and Marine Corps. And not only are we proven on all those aspects, we are also proven that we can demonstrate social impact and profitability can coexist. We do this, for example, through our IDEA program, where 1% of profits are donated and through a grant application format to businesses or to nonprofits and organizations in need. So, some of these are going to be batteries that we're sending off to schools, parks, or applications where the money isn't there to purchase the batteries, and we are able to help out and provide that social impact. It's also worth mentioning that we are manufactured in the US. There's a lot that remains to be seen about the recent IRA, Investment Recovery Act, that will show where manufactured in the US lines lie and potentially offer you increased incentives. So stay tuned for more on that as those develop. And it's in the name, simple, or simplify. We integrate into tons of different equipment that is existing and new. We do off-grid, grid-tied, standalone systems. We work with wind, solar, generators, the grid, you name it. What does all this do? Well, we're storing power for backup, for resiliency, and energy security, but we are also enabling customers to save money by using their batteries for time of use, peak shaving, and demand charge management, which we'll dive into all of those as well. UL listing. So what is a UL listing? Well, Underwriter Laboratories is a third party that performs tests to see if products are safe. And realistically, they test all kinds of things. And most things that you want to purchase should be UL tested to guarantee their safety. For batteries in particular, these are certifications around fire. So 1642 is the cell level test. These look kind of like a large AA battery in our batteries. So we're having a UL certification on the individual cell. 1973 is the battery itself, cube. And then 9540 is a certification that is based on a 9540A test protocol. So there's a lot of chatter about 9540A and 9540 and what that all means. We have an entire hour-long presentation on that subject. Spoiler alert, we did really well. The test results informed a 9540 certification that allows our product to be installed in municipalities like New York City that are very stringent about fire safety. And it allows our product to be installed without additional safety features. So some 9540A testing may indicate that, heat sensors or sprinklers or fire control systems or deflagration radiuses are required. Our product didn't have all that, so it can proceed without it. Why do you care? Well, UL certifications are needed for all kinds of things. Realistically, if you're getting a system inspected, your inspectors probably want to see that it's UL listed. You're going to want to check with your AHJ or authority having jurisdiction. Those jurisdictions are going to change the requirements. You might be dealing as an installation company with multiple different AHJs that have widely different standards. So it's important to understand those standards and how they apply so you can get your jobs permitted and installed and inspected. Like I said at the top, it's always a good idea to have a UL listing because you're talking about safety. If you want to bring something into your home that's not UL listed, should there be concern there? I'll leave that up to you. But if you have that UL listing, there you can be rest assured that the safety testing has occurred. Like I said, always check with your AHJ, and you may also need a UL listing for insurance purposes. And you may say, hey, Chuck, I'm off grid. I don't care. I'm not getting this permitted. No one's ever come into my property. Well, your property may be up for sale someday, and those UL listings may help the sale. So it's always a good thing to have if you can get it. So we have a problem. We've got a couple problems, but one of the problems we have is escalating energy costs. This is not a California specific thing. This is not a US specific thing. This is a worldwide thing. Energy is getting more expensive, specifically fossil fuel energy. We've seen increases historically year over year, sometimes multiple increases in a year from our utility pricing. We've seen the European market affected by, war and supply constraints, having their prices increase year over year, while they're simultaneously trying to do, green energy and phase out nuclear. There are, an existing dependency on oil that just keeps getting more expensive. It's a big problem. We also have failing infrastructure since, the grid was installed for the most part a long time ago. It's getting wear and tear. We are starting to see, in Texas, weather events where the grid simply cannot provide the power that everybody needs to get through a particularly cold spell. We're also having weather events where power gets knocked out, hurricanes, tornadoes, snowstorms. Overhead power lines are vulnerable. They get knocked out. And the grid is just aging. We're dealing with technology that 50, 60 years ago was good enough, but in the age of global warming, drought, high wind events, PG&E is turning off the power here just to keep fires from starting with their aging equipment. It's a big problem. And I mentioned global warming. There's a significant problem that we're facing here on this planet where changes to the environment are starting to affect everyone. A lot of us in the industry are really passionate that our work in renewable energy, distributed energy resources is part of the solution. What does that solution look like? Decarbonization. We're trying to get away from fossil fuels in general. We're trying to push renewable sources like wind and solar. And we're also electrifying everything from our homes, heat pumps, to our vehicles with electric vehicles. And we're really changing the way the world's going, which I think is pretty cool. Talk a little bit at the top about saving money. So there's several ways you can do this. When you're connected to the grid, you may have a rate signal or a way that the utility charges you that renewable energy or distributed energy resources, which would be like solar and a battery, can help offset some of the costs. So the first way would be peak shaving. In this graph on the left, we've got a couple peaks in purple. Those represent the highest amount power being used at an instant. So it looks like in this graph, there's a lot of demand right around lunchtime and a lot of demand right around dinner time, which makes sense. Well, how does solar and battery help? You can program your inverter to say, hey, I want to see my demand rate decrease by never reaching these peak demands. So as I say 5 kW is where I want to stay below, which is pretty high for most households. But as my usage starts to approach 5 kW, I can tell my inverter and batteries to go online and to handle my usage so that I never draw more than 5K from the grid. Therefore, I'm keeping my demand rates low because that demand rate, although an instant or maybe a 15-minute period of time, will be how the utility charges some customers for the entire month. So you have that one afternoon, it's hot, you got the game on, you got the AC running, you're making food, and that peak demand just for that short amount of time when all those loads was running would dictate your entire month of electricity bill. So peak shaving would be a great application to reduce those demand charges. Very common are time of use rates. The utilities have discovered or known all along that it's the most expensive time for them to make power is in the afternoon, when people are getting home from work. The available solar electricity that's being generated is starting to decline as the day gets towards the end, or in the winter, it's already dark. And everybody's starting to cook and turn on the TV and run their heat and AC and all of these things that are increasing the demand on the grid. And so the utility says, hey, we're going to charge you the most during these purple hours of the afternoon. Well, if you have energy storage, you can program it to say, okay, well, let's not buy electricity from the grid during the afternoon. Let's go ahead and, do what's called time of use arbitrage, where we're, either charging the battery earlier in the day off of low rates or solar, and then discharging the battery later in the day during high rates, so then we're not importing at that higher time of use rate. There also may be situations where, your solar, may not be valuable to export. There's changes to the California net metering agreement coming that are devaluing solar exports. And there are utilities that offer no export value at all. So if you're exporting solar to the grid in the afternoon where you're not home, the utility says, thank you very much, here's $0. And you're really losing the value of that solar. So in situations like that, you can take a battery, charge it up. We've got the purple curve here on the right showing a typical charging curve from morning, peaking around noon, and then just declining in the afternoon. So there's a bunch of solar there while you may be away and not using power in the home. So if I save all that solar energy in a battery, then I have it for later. And that's really accomplishing two things. I'm avoiding a low or non-existent export rate. And I may also be avoiding high time of use import rate. So a lot of ways that people save money.
That's a great point, Chuck. Thank you for explaining these. And what I always encourage people to do is understand is that if we are storing power that's produced during the day and using it in the evening, that we never actually use all of the battery's capacity to help save us money. We're always going to save a little bit in that battery just in case the power goes out that night, usually around 40 to 50%. And with our inverters, we can adjust that set point.
Yeah, it's a really good point, Daniel. Resiliency and the ability to have power in an outage is a huge money saver. If you lose power and have to throw away everything in your fridge, right? Like that battery could be paying itself off through avoided costs at the grocery store. We're here to talk about battery chemistry. When we talk about battery chemistry in this webinar, we're particularly talking about lithium-ion battery chemistry, which is a very broad term. There are other battery chemistries you may be familiar with. There's lead acid batteries. There's a lot of cutting edge batteries that are doing a lot of really different things, including really large operations that are, melting salt and storing energy that way. But we're not going to talk much about those. We're going to talk about lithium-ion. And we're going to, in particular, compare different lithium-ion chemistries. So in this graph, we've got several chemistries. We've got lithium iron phosphate in green. And then we've got 4 other chemistries that are all containing some form of cobalt. We've got NMC batteries, which are very common in home energy storage, cars. And then we've got some other chemistries that are also going to be used in mobile electronics, drones, as well. So when we look at these, we're obviously highlighting our battery here, but it's for good reason. I mean, we are safe. Like I talked about at the top, we do not have a danger of thermal runaway and fire, where all of these cobalt batteries do. We are not using a toxic element in that cobalt element. All these other batteries are. And no battery is truly landfill safe. If you have a lithium-ion battery that is at end of life, you should contact your local waste management or recycling program and see what they have for you as dropping off the battery and having it processed correctly. Don't throw them away. When we talk about the elements in a battery, we also want to talk about how those elements are extracted. Some mining methods are questionable in the way that they get the elements out of the earth and who's doing that. It would be worth stating that some of these practices are considered abusive to the labor that they are using. When we're doing an LFP chemistry, we don't have that problem. A lot of the elements we have are very widely available. Lithium is generally pumped out of the earth and then evaporated. Iron is incredibly prevalent on the planet. So we don't have these rare earth minerals that are causing abusive practices. We don't require ventilation on our product. We have a wide temperature operation range, where some of these other products will not have that range. And like I said earlier, may have some fire or safety risks that require additional equipment, like cooling equipment, maybe like through a radiator or a fan system or an HVAC. They may also require monitoring equipment to keep an eye on the temperature of the batteries so that these events never get started. Our batteries don't require any of that equipment. And like I said, we have a wide operating range, which we have a whole slide on. And yes, Alexander, lithium iron phosphate does not include cobalt. That's a good question. And it is one of the takeaways of this presentation is we are not a cobalt chemistry battery. It's very important to some consumers. It's very important for safety. It's very important for a lot of reasons. So when we talk about chemistries, these are some of the chemistries that are listed on the last slide. Again, cobalt is widely used in lithium-ion batteries. Not all of them use cobalt. LMO batteries aren't using cobalt, neither are LFP. There are also various form factors to consider. Like I said about our cells, they kind of look like a AA battery, although a little fatter. They're cylindrical. They have the anode and cathode spooled together with a separator that keeps the anode and cathode separate, but lets the lithium travel back and forth in charge and discharge. And they're generally in a metal case. Other form factors include a pouch cell. These are very common in cell phones, computers. They're lightweight, but generally they have the problem of being able to expand and contract, which isn't great for the cells. Over time, expansion and contraction can lead to degradation. Pouch is also inherently flimsy. It could be punctured. Another form that we're seeing more and more of are prismatic cells. So this has more of a rigid case, but it also is prone to some expansion and contraction. Similarly, both a pouch and prismatic cell have the positive and negative terminals at the same end, which to me lends itself to the possibility of a mechanical short. If something were to touch the positive and negative end, it could cause the battery to short out. So what are we doing? We're doing the lithium iron phosphate with a cylindrical form factor. We find this to be the safest chemistry and form factor, resulting in a high reliability and safety. So what is thermal runaway? Well, when a battery becomes hot enough, a chemical reaction can begin, and that can generate more heat, and that can accelerate the reaction. This is known as thermal runaway. So you heat it up enough that there's this chemical reaction, and that reaction generally results in off-gassing, which may be a flammable gas, which in turn itself has a thermal event. And now we've got runaway, potentially runaway with propagation. So if a cell were to experience thermal runaway and have a lot of energy, potentially some flame, that energy and flame could spread to the next cell and the next cell. And that would be an example of runaway with propagation. What we've got here on the right is a Samsung Galaxy Note 7 phone. These were previously banned from flights because the pouch cell in there had a propensity for thermal runaway. In this particular case, it was probably a single cell, so it wasn't necessarily expanding to other cells. I don't know that for sure, but it's not the, when we have a thermal runaway in a battery system, we've got cells, we've got batteries, maybe we've got battery units. multiple units, that propagation becomes very important. Well, what causes thermal runaway? Generally, it's a failure. This could be from a puncture as a result of abuse or a car crash, but it can also be other sources. Heat, a fire could cause thermal runaway, a short circuit, like I said about those terminals. So a short circuit either at the terminals or at the cell level inside the cell could cause it to go into thermal runaway. Overcharging the battery can cause it to go into thermal runaway. Anything that causes it to become an increase in temperature that is self-sustaining is thermal runaway. Now, when that thermal runaway continues to increase to the cell next to it, that's propagation. When we talk about lithium chemistries, thermal runaway is not universal. It is very different depending on the chemistry. There is a commonality in that in a lithium-ion battery, when thermal runaway occurs, the electrolyte will vaporize. So all the batteries have an electrolyte in them. You get it hot enough, it boils, becomes a gas. They all have a vent, and if that flammable gas vents, it has the potential to catch fire. If that gas is contained in the cell, obviously it won't. But if it does escape, it's not only flammable, it's also toxic. So when we talk about LFP, or lithium iron phosphate, we can reach a higher temperature before thermal runaway begins, which is good. So if we're not starting thermal runaway to, say, 200 degrees Celsius, but a similar product with an NMC chemistry is reaching thermal runaway at 170 degrees Celsius, that lower temperature means that that product may face thermal runaway more often or under less extreme circumstances. Further, when LFP does reach thermal runaway, it has a much lower maximum temperature than NMC. So if thermal runaway starts, the cell is going to go through an energy expansion, essentially, and we'll see that in the next slide. But then it kind of tops out at, say, about 400 degrees Celsius, where an NMC battery may top out much higher, about 675 degrees Celsius. So starts at a higher temperature and ends at a lower temperature. Those are good things. If the thermal runaway event is unavoidable, these things lend to a safer battery chemistry. Further, LFP releases fewer gases than NMC and other cobalt-based technologies. So a lot of theme here about safety in our batteries in these events. We've got some data to support this. This is from Sandia National Laboratories. What these graphs show you is they've got several different battery chemistries, LFP in the darkest blue, several other lithium-ion chemistries shown as well. On the horizontal axis, what they're doing is a controlled increase in temperature. They're taking all of these cells to hot, to very, very hot. And then on the vertical axis, what they're showing is as these cells start to get heated up, like I said, the electrolyte starts to boil and the off-gassing occurs. Well, when that off-gassing occurs, there can be a further thermal event. So the vertical axis is showing the energy of that thermal event as these batteries continue through this temperature range. Now, for example, with the green curve, we see that it starts very, very early, goes very, very high, ends very late. Similarly, the NMC curve in red, it's a pretty significant curve, not as high as green or blue, but we don't even see the LFP cell on this first scale. We actually have to zoom in 100 times to see the LFP curve, which again starts later and ends earlier. Not as dramatic of an off-gassing event, resulting in less energy from that boiled off electrolyte, potentially producing a larger thermal runaway event. So what this graph's really demonstrating is that, through similar circumstances of a high temperature, it could be a fire, that the LFP chemistry is far safer, that you're not going to have these high energy events with these big curves And in fact, the energy curve that you do get is rather small. Just as a note, all these slides will go out to attendees at the end of the presentation, and there are links. So you can actually click on this link at the bottom, and it will take you to this study where we're pulling these slides from. Is the primary flammable gas oxygen in a vaporized electrolyte? I believe the flammable gas is oxygen and the electrolyte itself. So if or not the electrolyte, but the cathode. So if you're using cobalt, you're not getting just oxygen, you're also getting cobalt in the off-gassing. And I believe that's what leads to the higher energy thermal event. Not a chemist. And if you want more detailed explanation on that, Jake, we can absolutely, we'll get with Nathan, who's on the training team here, who has a much broader understanding of the chemistry of these cells and what that off-gassing chemical composition would look like. So what does this mean for safety? Well, for a cobalt battery, you may need to have additional equipment. This could be, like I said, ventilation. It could be cooling like a radiator. It could be monitoring equipment. These are added costs for your customer. These are points of failure. These are moving parts, if you would. And often this is a parasitic drain on your battery. So a battery may have a heating and cooling system, right? That's great. It keeps the battery from getting too hot, may keep the battery from getting too cold, but those are all uses of energy. So your battery is going to have a drain on it by trying to control the temperature range. Because simplified batteries have that wider operating range, which we'll see, I believe, on the next slide, we don't need all this equipment. We don't need ventilation, cooling, or thermal monitoring. And if you're a solar person and you've been doing a bunch of MC4 connections and you're getting into energy storage and, you know, there's the challenges that come with that, the last thing you really need to be doing is trying to figure out, you know, how one of these thermistor and pump systems is malfunctioned, right? It's equipment you don't want to be messing with. Here's that operating temperature. So for our operating temperature, I want to clarify, this is basically discharge. Battery can discharge from -4 to 140 degrees Fahrenheit. Now, similar battery chemistries for lithium-ion products, like an NMC chemistry, may have an operating temperature of only up to 120 or so degrees Fahrenheit. So you're getting a lot more range on that high end. For charging, there is less of a brand-specific problem and more of a chemistry-specific problem in that lithium-ion batteries do not like to be charged when they're cold. The reason for this is that the lithium that's in the electrolyte, it's moving back and forth from the cathode to the anode, depending on charging and discharging. At very, very cold temperatures, that lithium can start to form little icicles. They're called dendrites. They look like the dendrites we have in our brain connections that are little branches. And when these lithium icicles form, they can actually start to damage the cells. They take up the lithium available and can potentially puncture or perforate the separator layer in the battery. So you never want to charge a lithium-ion battery at too cold of a temperature because of the formation of these dendrites. Again, this is not brand specific. This is lithium-ion in general. Now we'll see there's some exceptions that you can have a reduced charging rate at low temperatures to avoid that problem. But generally speaking, you don't want to charge a lithium battery if it's freezing. So wide operating temp range means no need for coolant, and then a charging temperature range that is rather typical. But it's a good lesson for, you know, anybody who's been doing a bunch of AGM batteries that are freeze hardy, that when you move into lithium, you need to be very wary of charging during freezing times. We're going to be using a couple of terms that I just want to go over here. They're opposites, essentially. SOC is state of charge. DOD is depth of discharge. So a 100% state of charge is a 0% depth of discharge. 20% state of charge is an 80% depth of discharge. So for our product, recommending that if you're cycling the product regularly, that you do an 80% depth of discharge. You can go to 90% depth of discharge or 100%. We'll still warrant our product for 10 years. We know that if you do go to 100% depth of discharge, you will still have 80% capacity of the nameplate of that battery at the end of 10 years. But we also know, and we'll go into this a little bit later, that if you cycle only to 80% depth of discharge, that you're going to get a whole lot more. So we'll go over that a little bit more later, but it's one of those terms to be out there because we're going to start throwing them around a bit. Just another aside, a ton of questions are coming in. Daniel will try and address them in real time. If not, we'll save them for the end. All of our Simplify batteries have a BMS system, or a battery management system. So what does a battery management system do? Well, it can accomplish several things. At the most basic level, our BMS is a form of overcurrent protection. If it sees too much current coming into the battery, it has the function to be able to open the circuit and prevent the cells from seeing too much current. Likewise, it is used to balance those cells during charging. So if we are within a acceptable charging tolerance, but some of the cells are already topped off and some of them need to catch up, the BMS can distribute that energy. Further, it can offer some short circuit protection, which would be, if it senses that too high of a discharge or potentially a short circuit is happening, it can open up the BMS. And in some of our more advanced products, you will see a digital BMS that has some of the temperature-related discharge capabilities I was referring to in our Amplify battery, as well as increased discharge capabilities over the nominal discharge rate. For example, our Amplify battery with closed-loop communications can discharge up to 100 amps, which is significantly more power than it would be for the same cells in a 5 battery. We also have an entire hour-long presentation on BMS. So if you're looking for a better understanding of what that means, check out our training page for more on that. One of the terms that we're going to use in batteries in general is known as the C rate. So generally speaking, the C rate is the rate at which a battery can charge. So a 1 C rate means that the battery can be charged in an hour. Conversely, it means that that battery could be discharged in an hour. Now, if you're coming from the lead acid side of things, you may be used to C5 rates, C10 rates, which means that that battery is not really going to be able to be charged in anything fewer than, say, for a C5 rate, 5 hours. Similarly, getting the energy out of the battery, to take that entire energy out is going to take you a full 5 hours. Well, because of our C/2 rate, that means that we can discharge our batteries at a very high rate. A 3.8 kilowatt hour battery can be discharged in 2 hours, which means during that time, you're getting 1.9 kilowatts, which is a lot. Bigger thing here for a lot of customers is that you can charge it quickly. So it's winter time, we've got some low sun availability hours in the Northern Hemisphere here. If you're charging from solar, you've only got so many hours in the day to charge those batteries up. Or maybe you're running a generator and, having that increased generator output for a shorter duration is going to be saving you on fuel costs. Instead of running that generator for 5 hours, you can get that charging cycle done in 2. Or maybe you're pulling from the grid and you want to avoid, having a whole lot of kilowatt hours during peak hours. You can get that charge done quickly. So it's really important to understand the C rate of a battery for design and also for functionality for your end user. What is it going to take to recharge this battery? How long is it going to take? And we'll have some examples of that in our design section later on. Takeaway here is that a relatively small battery bank can provide significant power. So, 3 of our 3.8 kilowatt hour batteries at 1.9 kW each can provide you with almost 6 kW. It's a fair amount. Another key feature about our batteries is scalability and expandability. Now, you may be used to some home batteries, lithium-ion batteries that are available in a 13.5 kilowatt hour chunk. And that's it. You buy them at 13.5 kilowatt hours and you stack them at 13.5 kilowatt hours, and there's no nuance. It's 13.5 in each building block. Well, ours are, 3.8 kilowatt hours. So it's a much smaller building block, giving you some flexibility on that system size. Maybe a customer really needs about 16 or 17 kilowatt hours. So 13.5 isn't going to do it, and 27 is going to overdo it. You can get to that energy level with our battery with more scalability. We can also scale up to basically anything. Your inverter is going to provide a power limit. It's the amount of power that it can provide to your loads. But you can keep adding our 5 batteries basically infinitely. As long as you've got battery cables and DC combiners, you can keep stacking them as big as you want to go. Like I said at the top, with our high voltage line, it might make sense to go to high voltage at a certain kilowatt hour value. But speak with one of our sales applications engineers. We'll help you understand, where that threshold may be for your project. The other scalability features are our batteries, as they start to stack, increase not only the energy or kilowatt hours that is stored, but also the power or kilowatts. So like I said, they're 3.8 kilowatt hour C2 rate gives you 1.9 kilowatts. And so for every new 5 battery you're adding, you're getting another 1.9 kW of power available, which can give you some impressive backup numbers pretty quickly. Another aspect is expandability. In certain battery chemistries, it can be not recommended to expand a bank after it's commissioned. Essentially, by expanding a bank, you are limiting anything you add to that bank's ability to the lowest common denominator, the oldest battery in the bank. Well, to a certain extent, ours is true, but ours, you can expand, we'd say up to about the 2 or so year mark, depending on usage. So you sell a customer a perfectly sized bank, it meets their needs for a year, and then they go through some electrification of their home. They put in a heat pump, they get an EV, they need more. Well, you can add to that battery bank.
A lot of times, oh, sorry, Chuck. A lot of times people can't afford to go with all the batteries at the beginning. And so that's another opportunity, is sell them a system, get them started, and then we can always add batteries to run power, some of those luxury loads, as I'll call them. And you mentioned it, you said 2 to 3 years, depending upon usage. Well, if these batteries are kind of just sitting idle, not really being cycled and just kind of being topped off, well, you could probably add additional batteries a little bit longer down the road, maybe into 3 years. But if you're cycling them daily, you're using these pretty hard, you're going to want to add batteries relatively sooner rather than later. And that's an important comment that I just wanted to pull out. Thank you, Chuck.
Yeah, absolutely. You're correct, Daniel, that depending on the use case, an expansion may be a good idea past that 2 year mark. That's kind of our benchmark, definitely for a battery that's being cycled regularly. A couple photos showing those features of expandability and scalability. On the left, we've got an airport that has 80 of our 5 batteries, 300 kilowatt hours of energy. It's impressive. On the right, we have a smaller system, started off with 8 batteries on that sunny island, and maybe the homeowner electrified, but for whatever reason, they wanted more. And so they added 8 batteries to the bank. They were able to use the same combiner and the same sunny island, but they've increased the gas tank of the system, if you were. Another huge feature, if you're coming from the lead acid, battery world, is maintenance. If you're doing lead acid batteries, you're probably familiar with watering your batteries, maybe shooting the electrolyte to see if they need more electrolyte, a fair amount of regular maintenance. Lithium iron phosphate does not require maintenance. It does not release gases. It does not have any work that you have to come do on the battery. Further, our batteries have a low discharge rate. So at about 1% a month, they will self-discharge if they're not connected to anything. So, breaker's in the off position, they're at their warehouse, or, maybe the project's on hold for some reason. Storing them is okay. They will ship at about 30% state of charge. So, I wouldn't want to have a battery sitting around for more than about 2 years, because if it was at the warehouse for a while before that, you could start to be in those very, very low states of charge. If that were the case and you got a battery that was a low state of charge and you knew it was going to be a couple months before your project got off the ground, we would just recommend charging it up. If you get that battery fully charged, you can absolutely let it sit. If it's waiting for more than maybe 6 months or a year, maybe give it another charge. But that is not the case with some other batteries, where if you let them sit, self-discharge rate may be much higher. So no maintenance. That's a huge selling point for somebody who's been used to working with one of these kinds of banks, where on the left, a whole bunch of L16 batteries, mess of battery cable, a whole bunch of temp sensors, and all these white caps that have to be opened up so you can water the batteries and check the electrolyte. Ton of work, messy work, dealing with battery acid. Got to have a schmuck and gloves and glasses and personal protective equipment. On the right, we've got a lithium-ion phosphate replacement for that lead acid bank. Not only does it look super clean, it doesn't require any maintenance of the batteries. So let's talk a little bit more about our products. The Phi battery is our workhorse. Like I said, it's a 3.8 kilowatt hour battery. Comes in 24 volt and 48 volt options. And these are simple parallel connections. You can scale them to your heart's delight. There's really no upper limit of the number of batteries that you can add. These were originally designed and are great drop-in lead acid replacement. So you go out to one of those banks, like in the last slide, the batteries have reached end of life, and the customer's tired of maintaining them, or you're tired of having that maintenance contract. Sell them some Simplify instead. It does have an integrated battery management system to keep the cells balanced and to provide those basic protections. And I should have said it earlier, those basic protections do not make up for a poorly designed system. They're more of a backstop for if something happens. And all of our products have a breaker. I love the breaker. It's a simple but brilliant safety measure where you can make sure that your system's de-energized at each battery if you need to do installation or maintenance or anything on them. Our Amplify battery. This is a more advanced battery management system. It has closed loop communication with a couple of inverters. So basically you're running Ethernet cables from battery to battery to inverter, and that allows the inverter to communicate with the battery. Because of this, like I said earlier, you've got an increased discharge of up to 100 amps DC. We've also got low and high temperature protection, where at those extremes, the battery is able to communicate to the inverter, hey, I'm approaching freezing, and I know I shouldn't be charging as I approach freezing. I need you to scale back my charge rate. I need you to govern my charge rate so that I don't damage my battery cells. A very cool feature. Because of the battery-to-battery communications, you are limited to 75 batteries in parallel. Still a significant bank. And we currently have integration with the SolarArc inverters and our Simplify ESS. Now, these integrations are going to give you some auto-populated set points, but not everything's going to be programmed for you. I like to say that there are customer expectation set points you still have to set. So, for example, depth of discharge. Do you want to do 80% depth of discharge so you get the maximum life out of those batteries? That's something you'd set. Or when your generator kicks in and for how long. Those would be some customer expectation set points that you would have to take care of. But a ton of set points are going to be programmed by the battery into the inverter, making an easier commissioning. And those include communications about state of charge, what kind of voltage ranges it wants, and max charge and discharge rates. We also have some smaller batteries, 12 and 24 volt, 1.4 kilowatt hours. These would be your, drop-in replacements for something that maybe is more mobile. They have an ABS case that some of you have been installing our product for a while, maybe too. They're great for these mobile and telecom applications where you don't need a ton of energy. You just need to provide that 12 or 24 volt continuous power. All of our batteries have a breaker and a BMS. We've also got a lot of smaller products. These are our expeditionary line, where we've got our Big Jenny emergency kit, where you've got basically a suitcase that has the battery and inverter in it, and then a solar panel that you can flip open and charge. The Little Jenny is a smaller version with no solar panel, but it'd be a great way if you had periodic outages. You can leave that thing plugged into a wall socket to top off. When power goes out, you've got power on the go. Maybe take it camping or tailgating. Big Jenny's suitcase on wheels size version, increasing the amount of power and energy available. And these are great for emergency response situations. We've also got some cabinets on wheels where you'll have a battery with an inverter. Again, you can leave it charged, plugged in to be charging. Power goes out, you've got power on wheels. And then a stationary version where our access unit has batteries and an integrated inverter all in one cabinet. We're going to have 9540A testing done on our Solarc and our Schneider units so that you can have a 9540 certification for this product, which is really a big deal for a lot of AHJs. You can AC or DC couple. We'll have a couple examples of that coming up. And it's outdoor NEMA 3R rated. We also have those same cabinets in just energy storage, no inverter. So these will be our Boss cabinets, where you've got a 6 batteries or up to 6 battery in our Boss 6, or up to 12 batteries in our Boss 12. These you might just need to pour a cement pad, mount them, and then run a home run out to your inverter. We've also got high voltage, like I said at the top, in containerized solutions, 480 volt. We've got a whole team dedicated to these projects. So if you have a project that might want to look at this option, please reach out to us. We'll put you in contact with that team, and they can give you a scalable, much larger solution in high voltage. And we are introducing our Simplify ESS. Thanks to Briggs & Stratton, we're able to create this vertically integrated ESS with our own inverter, our own battery, and monitoring. Because of this, we are able to offer a single warranty from a single company, single tech support call. It's all under one umbrella. Stacks in a 6 kW inverter. This is outdoor rated IP65 and stackable. So if 6K is not enough for you, you can put multiple inverters in parallel, all feeding from the same battery bank, and be giving yourself more power. You can stack up to 9 inverters for 54 kW, which is significant. And it has a screen. I'm a little old school in that I don't love that a lot of inverter manufacturers aren't including screens anymore. The screen is great, especially if there's not only a power outage, but the internet's gone down. A mobile app that requires cloud communications isn't going to help your homeowner understand their battery situation in an internet outage. Screen will. With the ESS, we have a new battery. It's the 4.9 kilowatt hour battery. It is outdoor rated, and it is wall mountable. Same chemistry, same warranty, all of the highlights of the products that we've been selling, but this is a new version for integration with our ESS. Has the closed loop communication, so you have that smart BMS in it. And then the app. The app is the way that the installer will commission and grant homeowner access. You can monitor your fleet. Homeowner can monitor their individual system. Very cool. I want to talk a little bit about levelized cost of energy, because if you're coming from the lead acid world, you're going to run into price objections because lithium-ion batteries are more expensive. And there's no two ways about that. But that's an upfront cost. So when we talk about a levelized cost, we're talking about the cost of every kilowatt hour I can get out of the system. So if your lead acid batteries were going to age out at 2 to 5 years and need to be replaced, that upfront cost gets more expensive each time you have to replace the bank. Further, if you have a system with very high degradation, so your nameplate value on day one is not where you'll be at, say, year 10. There are some hidden costs there where you're not necessarily getting that value of nameplate throughout the system life. A lower degradation helps you achieve a better levelized cost of energy. There's an equation. You could do this in front of the right customer, but we actually have a calculator on our website. So when you get the slide deck, you can click here and you can start factoring in all these different things. Am I replacing the bank? Do I need additional equipment? And actually find out what that levelized cost of energy per kilowatt hour for the life of the system will be. Spoiler alert, it's often, in fact, always going to be better than a lead acid bank. So, do the footwork, share with your customer why levelized cost of energy is an important concept for them, for the ownership of the system, and get them a simplified system. We're going to talk a little bit about battery sizing. We talked about depth of discharge. When we say 80% depth of discharge, we are anticipating 10,000 cycles. So again, if you take this battery down to 100% every day, you're still going to get 10 years of use out of it. And we still anticipate 80% of nameplate at year 10. But if you take this thing down to 80%, not only going to get year 10, you're probably going to get another 10 and then maybe half again out of this battery. So your life of the battery is greatly extended by reducing your depth of discharge by just 20%. So if you size the bank correctly, to say, okay, how many kilowatt hours do you need? How many kilowatt hours does my bank have? I'm going to 80% depth of discharge. You can confidently sell a customer a system that may live 20, 25 plus years. Couple different examples of where we'd recommend different depth of discharge. Like we were talking about earlier with expansions, if you're letting your battery sit there, you can cycle it pretty deep. So for battery backup, maybe a couple dozen instances of usage a year, 90% depth of discharge is great. But if you're off grid and you're cycling that battery every day, or if you're doing time of use arbitrage, cycling that battery every day, 80% depth of discharge is appropriate. Now, maybe for the peak demand example, where it's really only covering the peaks of your demand for a couple of minutes, maybe 90% is appropriate, depending on the load profile for that user and how far you anticipate them discharging that bank. But again, for a zero energy home that's living off their batteries, off grid or grid tied, if you're using those batteries every day, 80% depth of discharge is appropriate because you will get that anticipated 10,000 cycles out of it. When we talk about sizing a system, I talked a little bit about those kilowatt hour values and how that's important for your customer and knowing 80% depth of discharge, what those kilowatt hour values look like. But we also need to understand the kW, the kilowatt value that these batteries can provide. So on the left here, we've got an Outback Radian, looks like an 8048. So that is an 8,000 watt inverter. And if we have 3.8 kilowatt hour batteries, and we can discharge at a C/2 rate, each battery is again giving us about 1.9 kW of power. So 4 of them are not going to provide enough power that Outback could demand. So we would recommend a minimum size of at least 5 batteries to provide the power that inverter is capable of drawing. So you want to do the math and you want to look at that inverter's efficiency rate. So if it's providing 8,000 on the AC side, what does it take from the DC side to get that 8,000 watts? Then you divide that by the maximum discharge rate of the battery. In this example, it's 5 batteries. We can always have one of our sales applications engineers assist you with system design, but it's very important to make sure that you don't set up an inverter that is able to discharge more than your batteries are able to provide. Tons of calculators available on our website. You'll get a link to the slide deck, battery bank sizing, system sizing, lead acid replacement, that levelized cost of energy calculator. A little bit on installation. I realize we're up on time, so I'll go real quick. We've got manuals and spec sheets. Always read the manual. We've also got integration guides. They will go over the specifics of the equipment that you are tying into. So if you're working with an Outback system, we'll show you Outback set points the way that Outback names them. in the order they're presented. Super handy when you're commissioning. Check out our product documentation. When we are installing, because we don't have those deflagration radius requirements, there are no clearance requirements. You can put the batteries next to each other. You can use brackets, you can put them in a box. Really, the only thing we don't want you doing is putting them upside down. That can have the weight of the batteries in the BMS, and that's not a good thing. Obviously, you'll want to take in considerations like humidity, and we have an entire presentation on harsh environments, temperature control, so forth. We are going to wire all of our batteries in parallel. There will be no daisy chaining and no series of our batteries. So in this example, the red cable that goes rather directly here is the same length as this red cable that snakes all over the place. So we have equal length battery cables to either our common DC combiner or our inverter terminals. An example of a DC combiner, this is a Midnight 1000 amp combiner. So you've got a massive plate to tie a bunch of batteries into on the positive and negatives, and then out for the inverter. Always use a torque wrench. Our torque requirements are listed in our manual, and they're not as tight as you may think. And if you use an impact driver on a battery terminal, you are likely to snap that battery terminal off and void the warranty. So always use a torque wrench. Don't use an impact. Couple single line examples real quick. We've got a DC coupled system, a bunch of PV with some rapid shutdown modules, a gigantic combiner for a couple Boss 12s, and a solar feeding a backed up load center. Typical DC combination, but we can also do AC coupling, right? So here we've got microinverters on the roof, a little AC combiner feeding into an AC coupled inverter. Again, dual Boss 12 and DC combiner feeding some backed up loads. Another example that's worth noting is generator charging, where we've got PV on the roof, but like my house has got snow on my panels. So if I need to top off my batteries, I'm going to need that generator. And I did not mention it, but our ESS is generator and solar ready. So you can charge from the batteries, you can charge batteries from the generator or solar or the grid. All of this feeding your backed up loads. I want to real quickly touch on our Elite IQ program. What is an Elite IQ? Well, these are installers who are qualified and vetted from our company to be on our map. So there's an aspect of us advertising you. And there are also rebates where if you are using our product through our warranty registration process, you can get a $25 cash back per battery. So if you're interested in becoming Elite IQ, there are several resources available to you. You're able to show up on our map. So if somebody's looking for a Simplify in their area, you pop up first. And then there's a rebate program as well that incentivizes you to continue using our product. We've also got a photo contest where we love pictures of our installs and our customers' dogs. So if you have a good looking install, send us a photo. You can win $250. It's a rolling contest. So if your photo didn't win in September, we still have it, and we'll consider it for our upcoming IQ newsletter. Interested? There's a QR code right here you can scan. We've also got a link that'll go out with the slide deck at the end here. Application process is simple. You're going to talk with one of us, demonstrate that you have an install under your belt, and we'll get you in the program once we know you're qualified. We have trainings, not only like this live webinar, but we have trainings on our Blue Volt Academy or Power Academy through Briggs & Stratton. There's generator trainings, there's battery and inverter trainings. And I want to thank you for your time. I ran a couple minutes over, and for that I apologize. If you're here for NABCEP credits, email training@simplifypower.com with your full name, how you want it listed on the NABCEP cert. So if you're go by Bob, NABCEP knows you as Robert, be sure to let us know, because NABCEP may not accept the certificate if we don't list your name correctly. With that, we'll stay as long as we need to get through these Q&A, and I appreciate all of your time this morning.
Yeah, Chuck, thank you so much. We appreciate you. Great job. Thank you again. I got a couple of the questions. I'll just try and run through some of them, and then I might throw a few over to you. Ryan's asking, my rep told me that I could only run 3 batteries in parallel with the Simplify inverter. Is this accurate? Now, I want to mention that our new inverter with our new battery, the Phi 4.98, can actually be 3 batteries in parallel before you can daisy chain up to 4 batteries in parallel before you have to use a combiner box. And I will say that really there's no limit to the number of batteries you can run in parallel. But when we think about running in parallel, we're talking about conductors of the same gauge and the same length going to kind of that midnight solar combiner you showed. We have been allowing you with the new 4.98 batteries to daisy chain in parallel, right? What does that mean? Negative, negative, negative off one side of the bank, positive, positive, positive off of one side of the bank. And we do allow daisy chaining in parallel with our bus bars up to 3 batteries. So that's maybe where you're getting the 3 battery bus bars available. But really, there's no limit to the number of batteries you can run in parallel. And just keep in mind, never run our batteries in series. Next question is what is the output voltage of a 4.9 kilowatt? Now, I'm not sure if you're referring to the 4.98 kilowatt hour battery. A 48 volt battery runs anywhere from 48 to 56 volts nominal. And if you're referring to an inverter, obviously the inverter would output at 240 or 120. Let's see, will a recording be available to us online? Yes, everybody should automatically receive an email with this recording. Usually it takes about a day or maybe less than a day for the computer to compile the video. So everyone will. Are there any plans to integrate into automobile retrofits? And Chuck, I'll let you maybe take over here in a second. I don't believe so. Go ahead.
If you're talking about a car battery, car batteries have a significant start voltage or start wattage that they need to provide. So, your typical car battery has the ability to surge massively to turn over your engine. In those installations, I would not recommend a Phi battery because of the maximum discharge of 37.5 amps.
And if they're talking about a retrofit, maybe they're talking about actually ripping out the gasoline engine and putting in an electric engine with some of these Phi batteries. We don't warranty for that. Like I think Chuck's mentioning, even in these electric vehicle applications, there's a much quicker discharge rate that needs to be accounted for. So it's probably could be done, but that's not something that we're an industry that we're moving into. What else we got? Let's see, Chuck, do you want this one? How about if Vic is asking, if the thermal runaway occurs for an LFP battery, what is your recommended way to extinguish the resulting battery pack fire? And I'm gonna let you answer this, but I would say, really, we're not expecting to have anything to extinguish because our batteries are gonna self-extinguish, kind of put themselves out. I would, if it's cobalt, I wouldn't even try. I would call the fire department.
Yeah, I would say if there's a fire, call the fire department. Generally speaking, a thermal runaway event is not going to happen in our battery to the extent that you get propagation. We verified this through 9540A testing. It was entirely unremarkable and, quote, boring, where, the cell temperature was raised, thermal runaway was achieved, and it did not propagate. So, my answer to that question would be, if there's a fire, get the professionals in. I highly doubt it was the result of our battery, but let the pros take care of it.
Yep. Kurt is asking, in regards to lithium-ion chemistry, and particularly to LFP and the metal oxide chemistries, a solid electrolyte interface, SEI, is formed at the negative graphite electrode during charging. How does SEI affect lithium-ion intercalation to the negative anode during discharge, and how can SEI affect cell performance capacity fade? That's a great question. I am not qualified to answer that, Kurt. I'm gonna let Chuck have a stab at it, but if not, we can get that answer to you.
Yeah, Kurt, I would say, in all honesty, I don't know. I'm not a chemist. I do know that intercalation is a concept that Nathan with our training team, who's not on this call, is familiar with. And so, if you want to have this question answered, I would recommend emailing it to training@simplifypower.com. We could have Nathan and potentially one of our engineers look at it. There may be a little bit of intellectual property there that we can discuss, but we may not. But you know, I would say just by your question that you already know more than I. So
yeah, exactly. Nathan's been is one of our great. I've learned so much from him. He's an old professor from Cal Poly, one of our top engineering schools on the West Coast, and he can really dive into some of these chemistry questions. Bruce is asking, I think you saw in one of our pictures that some of our battery cables are not able to be put in conduit. What do AHJs say about this? Well, really, AHJs have to interpret the code the way they see it. And a lot of these cables that you might see, we can put them in non-readily accessible locations. So as long as somebody's not able to get in there, and you know, we're thinking about maybe a wiring trough, there's other ways to get these cables to where they're not going to be a hazard. But again, always keep it up to your AHJs to have them have the final say on this. How about this one? Paul is asking, can the small battery be used low capacity whole house backup, or does it require a critical load panel?
yeah, Paul, I mean, if you're going to do a low capacity whole home backup, there needs to be a load analysis, and you're going to determine not only peak power that's needed, but kilowatt hours. That question went away, so I didn't catch the second part of it, but I mean, in the right situation, maybe, but a thorough load analysis is going to be required to do any kind of whole home backup successfully.
Yeah, exactly. Or yeah, he's asking, or does it require a critical loads panel? And the answer is yes.
Yeah, I would go that way. If you were doing a single battery backup, you're probably looking at critical loads and, you know, isolating some of the larger loads to a non-backed up load center.
Yeah, and also the ability to load shed can also be another way if you're doing a whole home backup, and drop some of those off. Let's see.
Ruth asks, is 3.8 kilowatt hours at 80% depth of discharge? No, Ruth. So our 3.8 kilowatt hour nameplate is 100% of that battery. If you were to do 80% of 3.8 kilowatt hours, you would get 3.04 kilowatt hours of usable electricity before you'd hit that, or usable energy before you'd hit that low battery cutout at 80% depth of discharge.
Brian's asking, he's out in New York and with Con Edison, and you know, he's asking about the demand management response. So currently, you know, with our batteries, the batteries can work with many different inverters. We're inverter agnostic. Specifically with our new inverter, it's on the roadmap. We have the ability to simply push a firmware update to meet some of these demand management systems, right? So the hardware is already there in our inverters. Really, what we need to do is be able to have the utility talk to our inverter and control that, or use some sort of device that fits in there near the meter. So it's on the way, and it's definitely coming along. One last one there, Chuck.
Curtis, do you need to consider partial state of charge when sizing the battery? In other words, there may be cases when a battery is not 100% SOC when asked to discharge. Does this need to be considered? So again, if you're doing an accurate load analysis, you're going to be considering, you know, nameplate values. So if a battery is at 50% state of charge and the load profile is demanding more than that battery can provide, that's going to be an issue. I'm not sure if I'm misconstruing your question there, but, you know, state of charge and available capacity are directly related. So a 50% state of charge means you've got only 50% of those available kilowatt hours. It will not necessarily affect the availability of kilowatts in power. You know, a 50% charged battery can still provide 1.9 kW, but the load analysis is really going to determine, okay, you know, if I've got X kilowatt hours, I need a bank of Y size to cover that with an 80% depth of discharge and normal usage.
Yeah, if we didn't get that question right, please email us, Kurt, training@simplifypower.com. Thank you, Chuck.
Thanks, everybody, for joining today. Again, if you want NABCET credits, email training@simplifypower.com, or if you have any questions, you can use that email as well. We appreciate you joining today's webinar and hope to see you again soon. Take care now.